The first important property that I wanted to tell you about canonical transformations is that they form a group mathematically. Are you familiar with the concept of a group? A famous example are rotations. So the product of two rotations, or the consecutive application of two rotations, is again a rotation. For each rotation there exists an inverse rotation that brings you back to the original state. And there is a neutral element where you do nothing. That's also a special case of a rotation. And so this neutral element times an arbitrary rotation gives that arbitrary rotation. Now the same holds also for canonical transformations. When you perform a canonical transformation, you go from a first set of coordinates to another set of coordinates via a canonical transformation. And then you apply another canonical transformation going from these new coordinates to yet another set of coordinates. Then the total transformation is again a canonical transformation. Imagine the following situation. You have the phase space coordinates little pi, and first you perform a coordinate transformation to go to new coordinates capital pi. And then you apply to these new coordinates capital pi, you apply yet another coordinate transformation to go to coordinates capital pi primed. The first transformation from little pi to capital pi has a Jacobian associated with it. Let me call that J. The second transformation, going from capital pi to capital pi prime, has another Jacobian associated with it. Let me call that J primed. You might just as well go directly from the original coordinates little pi to the final coordinates capital pi primed. The Jacobian of that transformation is the product of J prime with J, the matrix product of J prime and J. So let's check that the Jacobian of this third transformation is really the matrix product J prime and J. What is the Jacobian associated with this third transformation? It's the matrix of partial derivatives little pi k with respect to capital pi I primed. That's the Jacobian of transformation number 3. Now we can write that as the sum over j partial little pi k with respect to capital pi j times the partial capital pi j with respect to capital pi prime I. This matrix element here, or this partial derivative, that is the matrix element j, j, k of the first coordinate transformation, transformation number 1. The second partial derivative is the matrix element of the second Jacobian. It's an element of the matrix J prime, and it's the matrix element Ij. But this is equal to, if I exchange the order, so it's sum over j, Jij primed j, j, k. So you recognize from this component notation that indeed it's the matrix product of j prime and j. Now let's assume that both coordinate transformation number 1 and coordinate transformation number 2 are canonical. So we suppose that 1 and 2 are canonical, meaning that both the first Jacobian, so J, satisfies the property that its transpose times this matrix A times J is equal to A, and also the second Jacobian, J prime, also satisfies this property. So J primed transpose A J prime is equal to A. Then I claim that the effective transformation number 3, going directly from little pi to capital Pi prime, that is canonical too. Now we just found out that this transformation number 3 has the Jacobian J prime J. So let's check. Let's take this effective Jacobian of coordinate transformation number 3, take the transpose, multiply with A, and then this Jacobian again, J prime J. This equals J transpose, J prime transpose, A, J prime J. Now we know, since transformation number 2 is canonical, that this expression with the underbrace, that this is equal to A. So what remains is J transpose A J. But this is, since transformation number 1 is canonical, this is also equal to A. So this is equal to A. And hence, indeed, the transformation number 3 is also canonical. So, canonical transformations form a group. And for the mathematicians amongst you, this group is related to the symplectic group. Let us look next at arbitrary Poisson brackets. We already know that is in fact the defining property of a canonical transformation, that it preserves the fundamental Poisson brackets. It preserves the Poisson brackets between the Q's and the P's. What I would like to show next is that in fact they preserve arbitrary Poisson brackets of arbitrary phase-space functions. So let's look at two phase-space functions, f and g. So let's consider first the function f as a function of the original phase-space coordinates little pi. In terms of the new coordinates, capital Pi, this becomes a different function, capital F, of capital Pi, defined in the following way. It's simply the original function, little f, evaluated on little pi as expressed in terms of the new coordinates, capital Pi. And likewise, the second phase-space function g as a function of the original coordinates, and then we associated with that a new function, capital G, of the new coordinates, which is simply the original function of little pi and the latter expressed in terms of the new coordinates. And what I would like to calculate is now the Poisson bracket of these new functions, capital F and G, and the Poisson brackets calculated in the new coordinates, capital Pi. We have our general formula for the Poisson bracket in phase-space coordinates, it's this double sum ij going from 1 to 2f, then this matrix element aij, and then the partial with respect to pi I and the partial with respect to pi j. Now the partial derivative of f with respect to capital pi I we can write in the following way. Let me start out here in the same way. 2f aij, and then we write, instead of partial of f with respect to capital pi I, we write that as the partial of little f with respect to little pi k, and then the partial little pi k capital pi I sum over all k. And we do the same for the second partial derivative that appears in here of g with respect to capital pi. We say this is the, we write that as the partial with respect to little pi l, and then times the partial pi l with respect to capital pi j, sum over all l. This here is an element of the Jacobian. That's the element j I k. This is another element of the Jacobian. This is the element j l. We can take the summation over k and l to the front and say this is sum over k l. Then we have here at the end, we have somewhere we have partial of f with respect to pi k, little pi k, and we have the partial of g with respect to little pi l. And let's look at the rest. We still have a sum over ij. We have an aij, we have a jik and a jjl. This one here, the jik, we can also say this is instead it's the element ki of the transpose of the Jacobian. And let's consider it in the following order. We take first j transpose ki, then aij, and then jjl, and we sum over I and j. And this is the KL element of the matrix product J transpose A J. J transpose A J, and of this it's the KL element. If the transformation is canonical, then this matrix product J transpose A J is equal to A, if canonical. If that is the case, then we have the sum over KL, and then A KL, and then the partials of the functions f and g with respect to the original coordinates, the little pi's. So by definition, this is then nothing but the Poisson bracket of f and g in the original coordinates, in the little pi's. And that is precisely what we wanted to show, that under a canonical transformation, the Poisson bracket of two arbitrary phase-space functions is preserved when you go from the old to the new coordinates. So we have now two properties already of the canonical transformations. They form a group. They preserve Poisson brackets, not only the fundamental ones, but arbitrary Poisson brackets. And now I would like to come to yet another useful property. They preserve phase space volume. And you can see that very easily, starting from the defining property of a canonical transformation. That's the requirement for the Jacobian. You take the determinants on both sides, and you find on the left-hand side you get the determinant of the Jacobian twice, so squared, times the determinant of A equals the determinant of A. The determinant of A is non-zero, so you can divide by the determinant of A on both sides, and you find that the determinant of J of the Jacobian must have absolute value equal to 1. This implies that when you consider phase space volumes, so you have in 2f dimensional phase space, you consider a volume integral d little pi. And now you go to new coordinates, capital Pi. How does the volume element transform when you change coordinates? The volume element is multiplied with the determinant of the Jacobian. Yeah. So in terms of the new coordinates, this is phase space integral 2f dimensional phase space integral with the new coordinates capital Pi times the determinant of the Jacobian, absolute value if you neglect sort of the possible change of sign due to changes of orientation. But for canonical transformation, we just found this determinant is equal to 1, or this absolute value of the determinant is equal to 1. So in fact, we find that phase space volume, the volume elements, are the same in the old and in the new coordinates. So as a further consequence, we find that canonical transformations preserve volume elements in phase space. So we've now already collected a number of interesting properties of the canonical transformations, a group property, preserve Poisson brackets, preserve volume. And now I want to show that they also preserve the structure of the Hamilton equations. Remember the Hamilton equations, which can be written in the form, now in phase space coordinates, the change in time of the phase space coordinate pi I equals the Poisson bracket of that phase space coordinate with the Hamilton function. And this holds for all indices I going from 1 to 2f. If we express the Poisson bracket, as we had done before, in terms of phase space coordinates, then this can be written in a very compact vector notation. If we take the phase space vector pi, then its time derivative equals our matrix A applied to the gradient of the Hamiltonian, where we now take the gradient in phase space. So it's the gradient not in position space, but in phase space. So this is a very compact way of writing the Hamilton equations. We can check that perhaps for one dimension, so you get some intuition for that equation. In one dimension, the phase space vector has two components only, q and p, and the time derivative of that, the time derivative of the phase space vector, has the components q dot and p dot. Now we know q dot equals the partial of the Hamilton function with respect to momentum, and p dot equals the partial of the Hamilton function with respect to position. We can write that also in the following form. It's the matrix 0, 1, minus 1, 0, applied acting on the vector with components partial of the Hamilton function with respect to q and partial with respect to p. And this matrix in front here, this is in one dimension nothing but our matrix A, and the vector here, this has components partial derivative of the Hamilton function with respect to the first phase space coordinate is the first component, the second component is the partial with respect to the second phase space coordinate. So it's nothing but the gradient of the Hamilton function with respect to the phase space coordinates. And you see that in one dimension? And you can generalize that to arbitrary dimensions. So this is a compact way of writing the Hamilton equations in vector notation, vector and matrix notation. Now, let's look at the coordinate transformation. And let's restrict ourselves to coordinate transformations that are not time dependent. So we go from coordinates little pi to coordinates capital Pi. And we say this is not time dependent. This implies when we write the change in time of a new phase space coordinate capital Pi, then we can express that in terms of the time derivatives of the original coordinates, and the transformation is simply with the help of the Jacobian. So it's the sum over I going from 1 to 2f. Then we have the partial capital Pi k with respect to a little pi I times little pi I dot. This is the transformation for the time derivatives of the phase space coordinates, provided the coordinate transformation is not explicitly time dependent. Again, you can write this in a compact vector notation. You can say that the phase space vector capital Pi, and its change in time, its time derivative, equals, and what you have in here, the partial derivative of the new coordinates with respect to the old coordinates, that's just the inverse Jacobian. We had defined the Jacobian as the derivatives of the old coordinates with respect to the new coordinates. Here we have new with respect to old, that's the inverse, and it's also the transpose, so we have the transpose of the inverse Jacobian applied to little pi dot vector. When we look at the gradient in there we have partial derivatives of the Hamilton function with respect to phase-space coordinates. So let's look at the partial derivative of the Hamilton function with respect to a new phase-space coordinate. This too we can transform with the help of the Jacobian. We can say this is the partial of the Hamilton function with respect to the original coordinate little pi I times the partial of the original coordinate with respect to the new coordinate sum over all I. And this again we can write in vector notation. On the left hand side this is a component of the gradient in phase space. So on the left hand side we have the gradient of the Hamilton function in phase space, and the gradient is with respect to the new coordinates, the capital Pi's. And on the right hand side we have the partial derivative of the Hamilton function with respect to original coordinates, little pi's. So these are components of the gradient in the original coordinates. So little pi on Hamilton function. And there is in there, on the right hand side, there is a matrix element of the Jacobian. So this is J. That's the Jacobian acting on the original gradient. Now let's combine all these ingredients. We have capital pi dot, so the change in time of the new phase-space coordinates. This is equal to, we know that's the transpose of the inverse Jacobian times little pi dot. So we have the inverse Jacobian transpose acting on little pi dot, but little pi dot we know from the box up there, that is the matrix A applied on the gradient of the Hamiltonian. The gradient with respect to the original coordinates. But the gradient with respect to the original coordinates we can express using sort of our last result. We can express that as the inverse Jacobian acting on the gradient with respect to the new phase-space coordinates. So this is the equation of motion for the new phase-space coordinates. So we combined three ingredients. We combined the equation of motion in the box. We combined we used the expression relating the capital pi dot to the little pi dot, and we used the expression relating the gradient with respect to capital pi to the gradient with respect to little pi. These three results we combined into this one equation. Now this matrix product in this blue circle, if the phase-space transformation is canonical, then this matrix product is once again equal to A. The original condition for a transformation being canonical was J transpose AJ equal to A. You can multiply from the left and from the right with the inverse, from the right with the inverse of J, and from the left with the transpose of the inverse of J. And then you find A is equal to what's written there, the transpose of the inverse times A times the inverse. Okay? So if the transformation is canonical, then again you have the A here. So in that case, this is equal to A gradient with respect to the new coordinates times the Hamilton function of the Hamilton function. So in that case, if the transformation is canonical, you see that the equation of motion for the new coordinates has exactly the same structure as the original equation for the original coordinates, with the same Hamilton function. So in that case, the equation of motion has the same structure. And the same Hamilton function. I should add a warning here. I should say that a crucial assumption that we made was that the coordinate transformation was not time dependent. If the coordinate transformation is time dependent, then the Hamiltonian is no longer the same. And we'll come back to that later, and I will show you how in that case the Hamiltonian changes. When the canonical transformation is time dependent, then we will show later that you still have the same structure of the equation of motion. So still it is true that the change of the coordinates is this matrix A applied to the gradient, but now in general of some different Hamiltonian H prime. So where in general this H bar, this H prime is different from the original Hamilton function. And this is something that we will investigate later. So yet another interesting property of canonical transformations: as long as they are time independent, they also leave the Hamilton equations invariant.